Hi people. Yesterday I prepared a video segment on some tips for plotting stresses using solid elements. Okay, uh, and the reason I did that is my plan is to make a few segments on analysis of composite laminas, composite parts using the Catia's FEA native FEA solver. In order to do that, I have to set the stage for doing a bit of uh, things that are not quite well documented in CATIA, and those are plotting stresses. And I did the solids first, and now we're going to be doing the shells. Uh, this is more pertinent to composites because composite is made of a stack of plies or laminas, and uh, the direction of the fiber in each of these is different, and therefore we may want to plot the stresses using different coordinate system. But anyway, the problem that I did earlier with solid elements was something like that. It's a very simple problem. It's a block on the uniaxial load, and you see here three coordinate systems that I'm going to be using, or I did actually use when I did the solids, and I'm going to be doing the same thing here, except that we are now going to model this thing with shell elements. Okay, so here's the situation. That block is represented by what you see here on the top right corner. However, because of the symmetry, we need to model only a quarter of that basically surface. Okay, so the situation, the quarter of the surface is shown down here, so 4 inches long, 1 inch wide, because remember the original part was 2 by 2, 1 inch wide, and the thickness of this shell is going to be 2 inches, which is the height of that block that you see. And the coordinate system are shown here. Oh, by the way, the load was specified as 100 psi on the right face, Now, because you're using shells, we don't use psi. We're going to be using basically psi per inch. Okay, uh, I'm sorry, not psi per inch. This is wrong. So we have lbf per inch. Okay, so if you look at it, 100 psi acting on a square which is 2 by 2, so that's going to be 400 pounds. Now, because we are using half of this half of the width, so 200 pounds is going to go on the piece that you see on the that's going to be modeled. But because we are using shells, we're going to specify that as 200 pound per inch. Okay, over the 200 pounds over that inch. Okay. Now, the coordinate system, I created one coordinate system which is aligned with the global coordinate system. This is the one that I created, but it is aligned with the global XYZ. Then there is one here where the coordinate system is rotated about the z-axis, the original z-axis, by minus 30 degrees. And then one that the y coordinates, the coordinate system, this original coordinate system, is rotated by 45 degrees about the y-axis. Okay. Uh, Let me go ahead and show you the next slide. So here's the situation. This is the same thing that you see on the other transparency on the other slide. However, I've made a comment here that this will turn out to be meaningless for the case of a shell model. Okay, and right here, meaningless for the case of shell model. Okay, so let's go ahead and model this thing in Catia. All right, so because I'm dealing with surfaces, let me go ahead to generative shape design. And on the XY plane, I will sketch a line on the x-axis, which is 1 inch long. exit, and I'm going to, this line that I drew, I'm going to extrude it by 4 inches in the direction Y, 4 inches in the direction Y. So you put the cursor there, right click, 4 inches. Okay, so what you see there is really this piece, okay? Now, for a reason that hopefully will become clear to you later on, I'm going to join this, okay? You can go ahead and do the problem without joining it, but I already mentioned in the video segments that were posted on November 3rd, 2020, that if you join, then you can assign a direction to the surface, a positive or negative direction to the surface. And this dictates the coordinate system, local coordinate system that appears as a shell element. So I'm going to join it, this, and notice that if I double click on this join, you get an arrow. This arrow means that this is the positive normal to that surface. A surface has 2 sides. One is the positive side, arbitrarily decided the positive side, which in this case is the top. And then if you flip it, it's going to go down. So then this becomes negative, the other side becomes positive. Okay. So right now I'm going to keep it the way it is. All right. Oh, let me go back here. When you do shell element, when you mesh this thing with shell elements, the elements have a local coordinate system which are actually opposite to the direction of the normal. So what I want to do is I want the normal to my shell elements to be upward. That being the case, I'm going to flip this. Remember, the direction of the z-axis for the local element is opposite to direction of this joint. Okay, so there we are. Okay, so let's see now. Save this thing, file, save management, save as. I already have a folder there, which was called shell something. Shell November. Oops, no. Solid shell stresses. This is your shell November 11. I'm going to put this thing there. Okay, that's fine. No problem. Okay, so let's apply some material to this thing. Metal, steel on that part. Okay, also I would like to create these coordinate systems. Okay, I already did this thing once in the earlier video on solids. Now this is the second time we're going to do it, which is good practice. Let me see now. The coordinate system is right there. You see this? This is how you create a local coordinate system. Okay. So the origin, by default, it puts it as a global origin, which is right here. But no, I want to move this thing a little bit to the left of it. So in the x direction, I'm going to say create a point whose x coordinate is, let's say, -2. Okay. See, there we are. So I'm going to get the coordinate system there. Actually, let me make this thing -1. So it's going to create a coordinate system here. Okay. And okay. And notice that by default, this is aligned with the global coordinate system, which is XYZ. Okay, so that's one. Let's do another one. So another coordinate system. Create an origin, create a point. So let's go to -2. Where's that going to be? Okay, so this -2 is measured from the original point, which was down here. And let me make this thing -2.5. Okay, all right. You say okay. Now, this one, I want it to be rotated about the z-axis by -30 degrees. So I put the cursor there, right-click, rotation, -30. -30. There we are. You can see that. Notice that one of these is dotted. That means that the solid one, which is right here, is actually the current coordinate system. Now, I don't want this thing to be the current coordinate system because the next one that I want to do is going to be rotation about the y-axis, not the y-axis of the one that I just created, but the original. So what I can do is I can say, okay, so let me deactivate this. Deactivate means put the cursor on it, right-click, and say set not as current, set as not current. Notice that they're both now not current. So let's do another coordinate system. Again, notice that it does from here. So right click, create a point. Let's go to -5, right there, and say OK. And this one, we want to rotate about the y-axis. So we put the cursor there, right click, rotation, 45 degrees. 45. OK, good. Now, I don't want this thing to be current either, so set not as current. Okay, we're done here. All right. Now, what I would like to do, by the way, it makes my job easier. I'm going to rename these things. Properties, so I'm going to say this was aligned with global XYZ. The other one, right-click properties, rotated by -30 degrees about global Z. And the last one, right-click properties, rotated by +45 about the global Y. Okay? This is just for bookkeeping purposes. So we're done here. Let's go ahead and save it. We're going to go to let's see now, analysis and simulation. If you want to do a fancy rectangular mesh, you can go here, advanced meshing tool, and use a surface mesh, etc. But that's really not the point right now. If I have the time, I'll do that for you later. Well, I can mesh this thing in the global generative structure analysis, because I'm not going to use a fancy mesh. I'm going to be using only a triangular mesh right there. So we're going to triangular mesh right there. Click on the surface. Okay. And well, let's use a parabolic element. That's fine. But the size, I'm going to make it 0.1, maybe let me make this thing 0.125. Let's see how it looks like. Yeah, 0.125. So if you want to see the mesh, right-click, mesh visualization. Here's the mesh. You can see that. Okay. Now, I want to show you something here. If you put the cursor on this line, nodes and elements, right-click, generate image. You click on generate image, and I can do a whole bunch of things related to the element. For example, I can say, show me the local axis of the element, okay? So I say, okay. So what happens here is, let me change the background color here. Tools, options. Just bear with me for a second. So it shows you for each element, you have a local coordinate system. 1, 2, 3. 3 is up because remember, I flipped the direction of the joint arrow so that 3 goes up. Okay, and why I did this, because when I say rotating about the z-axis, remember one of the coordinate system was rotating about the z-axis by -30 degrees. Now that means that 30 degrees that I'm referring to is this with respect to this z-axis, which is also pointing up. Okay. All right. So you can display the local coordinate system for each element by creating this image. Now, if you don't want this thing, you can delete it or deactivate it. Okay, there we are. And I'm going to change my I'm going to change my background color because the coordinate system do not show. You can see it's right there, but because I changed the excuse me changed the background color, you can see it. So let me put it back to what it was. Oops, tools, options, color. There we are. Okay. All right. Now we're going to apply our restraints. Oh, the thickness. The thickness is a 2D property right there. See that? You click on it, you select it, and you put 2 inches there. There's a 2-inch thickness. 1 inch up, 1 inch down below the surface. All right. Now, as far as the load is concerned, we're going to apply a line load first, line load density. So it's this, and I'm going to change that to, it was 200 lbf underscore ing, which turns it into this number. Okay. I tried to set the units, line load units in the options, but there is no such a thing. You have to put it write it as lbf per inch, and then it's going to automatically convert it to Newton per meter. Okay, very good. So that's good. Oh, the direction is positive y. So in fact, you can see what happens here, right there. See this? Positive y direction. And we say okay. Now, this is a line of symmetry or a plane of symmetry. So I'm going to say user defined restraint. And let me remind you about the rule for setting the symmetry in shells. So this line is a line of symmetry and lies in the global ZY plane. That means it does not move in X. So because it lies in the YZ plane, there's no motion in the X direction, and rotations are exactly the opposite. So this was checked, the rotation is unchecked, these two are unchecked, and rotation must be checked. Okay, and then we do it on the other side. Make sure that you hide this. If you're doing it the way I did it, you hide this line. There was a line here, because if I put a restraint on that line, Catia will not see it. So let me do a user-defined restraint. Let me uncheck all of these. This back edge lies in the XZ plane, because it was by symmetry XZ plane, so it does not move in Y, and rotations are exactly the opposite. Okay, now it looks like everything should be okay. However, when I run it, you see that it will bomb out, and I have to go to fix it. So let me run it. It will bomb out. There. And the reason, if you want to know what the reason is, you can still plot the displacement or the deformation, and notice that it moves as a rigid body up and down. So what I really need to do is one corner point, I have to prevent it from going in the vertical direction. So let me rewind this thing and make sure that you reset the scale here. Well, actually, let's go ahead and deactivate this plot. We'll do that later. Deactivate the plot. And then go and take one corner point. It really makes no difference in this particular problem. So, for example, this corner point, I'm saying, don't move in the Z direction. Don't move in the Z direction. Okay, if I run it now, it will be okay. Okay, and then if you look at, for example, the displacement, let's look at the stresses. There we are. Okay, and let me change the rendering to material shading. There we are. Okay, don't let these things fool you. Don't let these things, these weird red dark red spots fool you. Look at the numbers. Everything is 100. Okay? Therefore, as I expect, the von Mises stress, the only stress that's acting in this problem is the stress in the x direction. Okay? There's no other stress in y direction. There's no stress in x, z, or there's no shear stresses. Okay? So it's not surprising that the von Mises stress is also 100. Now, let me deactivate this. Actually, I'm going to delete it. Okay. Okay. So here's what we're going to do. I put the cursor on static case solution right there, where the graphs are all stored, and right-click and say generate image. It says, what kind of an image do you want? Well, I want stress, so let me filter it by stress. Okay, it says, what is it that you want to plot about the stresses? Well, I want the stress full tensor component. Now, stress full tensor component. Now remember, stress in general has 6 components, but when you're doing shell elements, the assumption is that the stress is through the thickness, and both normal and shear stresses are 0. Okay, so we say okay, and we get something. The question is, what is that something? Okay, so first of all, let me get my coordinate system here. I put the cursor on part right here. Show me these. Okay, fine. I don't want the actual surface, so I'm going to hide it. Let me hide the surface here. From the tree, it's easier to pick it from the tree. It was joined, right? Hide this. There. Now, what is it that we have plotted? So I'm going to double click on this thing again. See that? The one that I generated, double click on it again. And I say more. Now it says that the coordinate system that it's using is local Cartesian. Now local Cartesian, you know what it means, but local is referring to the local element directions. Remember those 1, 2, 3 axes that I plotted here for you? There were a zillion of them. Okay, and the 3 is up. 3 was up, but 1 and 2 were kind of randomly oriented. It's not really randomly oriented, but my point is that changes from point to point. That's why it looks like that. As a matter of fact, if you go here and you activate this 2, this was the local axis. So if you activate that, oops. Okay, well, actually, if you just say, show me those directions, display local, if you zoom in, you see that you get 3 up, 1 and 2. Well, it kind of varies from element to element because those are the local element directions. So uncheck it. That's why it looks like this. So I really, in this particular problem, I don't want to show the stuff in the local direction. Well, first of all, I can show it in the global direction. All right. Now, what am I plotting here? C11. Remember, this is a shell. There's only 3 components of stress. Two normal stresses in the plane of the shell and a shear stress in the plane of the shell. Okay? So it's not 6. Now, this is all I get. If you look at C11 that I'm plotting, is the stresses in the direction, global direction X. 1, 1, global direction X. Now that is 0 because I'm pulling this thing in the y direction. If you go to C22, you get 100. These are all 100. You can see that because this is the stress in the direction, global direction y. C22 is the global direction y. If you look at C12, oops, where is that? C12, that's shear stress, which is 0. Look at these are all 0, very close to 0. Okay. By the way, because we're using shell element, you can show the stresses on the upper, mid, and lower section, or both at the same time. But in this particular case, it makes absolutely no difference because there is no bending involved. If we are pulling this thing in the plane of the shell, there is no there's no variation from the upper surface to lower surface. But if you were doing bending of this, then of course what you get in the upper, mid, and lower surfaces are going to be different. There was a video segment on this some time ago. I don't know where it is, but you can go check it out if you want. This issue will become very critical when we do composites. Okay. Now notice that here, let me put this thing on C11 again. Here you have a choice. This was the global one, but we have a choice. Remember, we have 3 coordinate systems that are created. This one is aligned with the global coordinate system. So if I select this, it makes no difference. It will be exactly like what we see here. So if you say choose user, and for user, if I select this, nothing will change. Just watch these numbers, whatever they are, they're not going to change because the coordinate system, put the cursor there, the coordinate system XYZ, the first one here, is aligned with the global, or nothing changes. But let me go and select the other one next to it, which was rotated about minus 30 degrees by minus 30 degrees about the z-axis. So let me go ahead and select user, but this one now. Aha! If you go and watch the video segment on solids, you see that C11 was 25, C22 was 75, and C12 is minus 43. Now, I'll put this thing back up, so it's disregarding this slide. So you see that 25, 75, minus 43. Now this you could have, you can get this information based on Morse circle too, but notice that I didn't use the Morse circle. I asked Catia to directly calculate it for me. So fine. Now, what if I selected the other one? So let me see now. Let me show this. Okay. What if for coordinate system I had selected as the user this last one? In other words, rotating it about the y-axis by 45 degrees, and you will see that it actually gives you back the one for the global directions. And why am I saying that? I selected different coordinate system, but it gave you exactly what I got from coordinate system 1 or the global coordinate. It gives you exactly the same thing. And let me tell you why. You see, for this one, it says this is meaningless for shells. Okay? This rotated coordinate system by 45 about the y-axis is meaningless. And to make a point of that, I'll go down here and show you the slide. Okay? Only rotation in the plane of the surface makes sense. In other words, about the z-axis. Another way to say it, only rotation about the normal axis to the surface of the shell makes sense. I live on the surface, so rotation about the z-axis, normal to the surface, is all that matters to me. Okay. Now, there is this last one. This is basically saying the same thing. So this is not going to do you any good because it won't give you any numbers. It will give you the actual global stresses. Now, in continuation of the problem that I did with solids, I'm going to do another one, because notice that, let me see for a second, double click on this, more. Now, you can also select a manual one. Manual one means do it on the fly. For example, I can go and make this thing 0, this thing 1, and this thing 1, this 0. That means a 90-degree rotation about the vertical z-axis. Now, when you look at the 90-degree rotation about the vertical z-axis, basically I'm swapping x and y. Okay, so we say okay, and notice that C11, which was 0 before, is now become 100, because C11 is really your which is CXX of the coordinate system that I manually on the fly created, is along the line where the load was applied. Okay, and C22 becomes 0. This was exactly the opposite when I did the global ones, for example. And of course, C12 is going to be 0. Okay? So I think this paves the road for the analysis of uh, laminated composites in Catia with the native solver in FEA solver in Catia. Good luck.